Good morning, and thank you for joining us here at the Future Panther Academy. My name is Bonnie Fujiasco, and I serve as the Special Events Manager for the Alumni Association at the University of Wisconsin-Milwaukee. Welcome back to all of you that joined us last week. We had UWM alumni and kids representing 47 different states. Isn't that cool? And we want to say hello to all of our new viewers this week who are joining us as we present the second program of our new 8-week series. It's called Stars Have Stories. And we are doing this in partnership with the UWM Planetarium. Our program host, Dr. Jean Creighton, is an astronomer, and she has been the director of the planetarium at UWM since 2007. So today's episode is called, Where Are the Stars? And if you're watching today's presentation live right now as I'm talking, you can send your questions to Dr. Jean using the chat box. You'll see the little chat box to the right of your video as you're watching us on YouTube today. At the end of the program, Dr. Jean will answer as many questions as she can. And, whoa, speaking of questions, last week we received so many questions, and they were great questions, but we just didn't have enough time to get to all of them. So what we're going to do is have a special episode at the end of the series. We're going to call it a mailbag series, where Dr. Jean is going to look into the mailbag, pull out questions that we couldn't get to during our previous episodes. So stay tuned for that. We'll let you know what that date will be. So now let's all settle in and get ready as Dr. Jean presents this week's episode called, Where Are the Stars?
Thank you, Bonnie. I'm so excited to talk to you about where and how to find stars in the sky. We talked about what we might be able to see at nighttime and the daytime last week, but now we're going to actually look for specific patterns in the sky and talk about where they are and how they change with time. So let's start then. Our next constellation that we talked about is based on the Big Dipper. In fact, I'm going to use the Big Dipper as our reference point to find many other constellations that we can see. So the Big Dipper, as I described before, looks like a shopping cart with a long curvy handle. If you look at the front of the shopping cart, and in the real sky, you can get about 2 fingers between those 2 stars, and you move your fingers about 4 times or so, you're going to find the North Star, also known as Polaris. This is probably the most useful star because it's directly above north. If you can see the North Star, then you know exactly if you're facing it, you're facing north. What's even better, I think, is that the angle between the North Star and the north point on your horizon is equal to your latitude, which means that if you were lost at sea, if you could see the North Star, then you would know how far you are from home roughly, which made that's one of the reasons why people got so interested in looking at stars. Now that's the Big Dipper, and notice that there's the North Star is at the tail end of the Little Dipper. On this picture that we have, they use the more formal names, Ursa Major, which in Latin means the Big Bear, and Ursa Minor is the Little Bear. The Big Dipper belongs to Ursa Major. Let's see what else we can find if we can spot the Big Dipper, what other constellations we might be able to see. If you carry on from the middle of the Big Dipper and connect it to the North Star, keep going, you're going to bump into Cassiopeia. That's a tricky name, so I'm going to cut it into 3, and I'm going to invite you to repeat after me. Cassie, O, Pia. Cassiopeia. She looks like a W or an M, and she's always visible at our latitude. So if you live anywhere around 40 or 45 degrees, even a little higher than that, you're always going to be able to see Cassiopeia no matter what time of year it is. I'm also pointing out Cepheus just because he looks like a stick house. That's the king. That's the husband of the queen. And I'm going to invite you to make a little square with your hands. Notice what I did here, and put a little roof on top. This is the shape of Cepheus. All of these are visible all year round. Now I'd like to show you how to find from the Big Dipper my favorite constellation of spring. I mentioned it last week. We talked about Leo. Leo looked like a backward question mark. And I'd like you to imagine that our little shopping cart has a leak. We filled it with water and it's dripping. If you imagine gravity pulling down from our lovely shopping cart, the water is dripping on Leo and it's making him mad. And we practiced last week what lions say when they get mad, right? That's Leo. Leo is, as I mentioned, my favorite my favorite spring constellation, because it tells me if I can see it early in the evening on the eastern horizon, spring is around the corner. And since it's the 1st of May, I guess really we are in spring fair and square. Two more stars that I'd like you to know because they are bright, and one of them especially is particularly cool. We talked about using the Big Dipper to find the North Star. If we use it downward, we can find Leo. Now we're going to follow the arc or the tail, if you will, of the Big Dipper. So here's what I'd like you to say after me. I'll say those two stars once, and then I'll tell you the mnemonic. Hopefully that will help you find these stars again. The names are Arcturus and Spica. Those are tricky names to remember, so here is how this might help. Arc to Arcturus. So you say it. Arc to Arcturus. Good. And Spica. Your turn. Okay, now together. Arc to Arcturus and Spica. Arcturus is the brightest star in the constellation of Boötes. He looks like an ice cream cone. Big blob of ice cream right here. And Spica is the brightest star in Virgo. She's supposed to be a young woman, but actually she looks more like a squished box. Imagine a box that got dropped in delivery and got kicked in. It looks a little bit more like this. Arcturus is particularly cool and clever because it's an alien star. You might say, what do I mean by that? When I say alien, I mean it didn't grow up in the Milky Way. It didn't grow up in our galaxy. It's a star that our galaxy grabbed from another galaxy, and we just took it for our own. So that's the only star you can see without a pretty serious telescope that did not grow up in the Milky Way. How cool is that? Now, all of this got me so excited, and it made me realize how much I miss my own planetarium at UWM that I thought, you know what? Last Saturday, it was a cloudy day. I'm going to make my own. So I'd like to show you my own planetarium, and I hope that that will inspire you to make yours. I put a bunch of chairs together, and they were facing each other. And just so that I have a small enough circle that a blanket can cover it. It's helpful to have a bright blanket, something really white. And you'll see my favorite little stuffed animals on the top there, our little friendly tiger. This was big enough for me and my son, who's almost 18, to be in. And let me show you the constellation and how I projected it. So you can use a flashlight. I used my phone because I found it worked quite well. I used a Post-it. You can use any kind of paper. And I used, with the help of a grown-up, you should take a sewing needle and just make little holes in the paper, and that projects. I hope you can see it. Projects. We'll need to show the little with the sewing needle, and then I hope you see in the background the Big Dipper projected. This is a very low-tech planetarium, and I will send you instructions later about how you can make your very own. I remember how much fun I had with boxes, making cool things inside them. So you should have fun with a planetarium as well. All right, so we talked, also, of course, you could use other things to make to make constellations. And again, I'll send that to you later on today. The thing about constellations, since we project them on one surface, is you might think all the stars of a constellation are at the same distance. And generally speaking, that's just not true. In this case, we see a three-dimensional projection of the Big Dipper, and some of them are only 60 light years away, and some of them are more than 200 light years away. Hold on, Dr. Jean. What is a light year? A light year is the distance that light travels in 1 year. That's a long way, considering that the sun is only 8 light minutes away. The light that we get from the sun has been traveling for only 8 minutes. So that gives you an idea of how far these stars really are. So far, we've talked about static stars, right? What do I see instantaneously? Let's imagine that we have time on our hands, and in fact, that we can stay up all night. What would we see? This is what we call a star trail. Imagine having a camera that can stay open for a long time. You would see the marks that stars make as time goes on, because the stars seem to be making circles in the sky. And I hope you also notice that somewhere right there in the middle, there's a little dot that hasn't moved much, and that's the North Star. The North Star, because it happens to be directly overhead, our North Pole, isn't going to look like it's moving much. Think about it. As the Earth is spinning around, everything in the sky is going to look like it's moving in the opposite direction. But if we were to look up at that one star, that's going to stay put. This is an apparent motion. The stars aren't really doing that. It just looks that way because we are spinning. What if we had lots of time on our hands? What if we looked at stars for weeks on end? We would notice that sometimes we can see some constellations and sometimes we really can't. So what I've done here is I've put, again, I'm not showing you that these stars are at different distances because it doesn't look that way to us quickly. So I'm just imagining that we put all the constellations along a certain club we call the zodiac all around us, and that the little blue dot there, is going around the sun. What you'll notice is that the Earth, if it's looking toward the sun in this picture, you'll see that the sun is in the direction of Leo. Well, that means I can't see Leo if the sun is in that direction, because as we've talked about before, the sun is so much closer to us that it's going to make other stars way too dim for us to see. So there are going to be times right there where we can't see Leo, but the people who are on the night side of the Earth will be able to see easily Aquarius and Pisces and Capricorn. One of the zodiac constellations that doesn't normally get shown here is Ophiuchus. If your birthday is between the 30th of November or the 18th of December, the sun is going to be in Ophiuchus. And I guess the reason that we don't count Ophiuchus normally is because Babylonians didn't like much the number 13, so they nixed Ophiuchus and they kept the other 12. Let's talk about what if we had a whole lot of time? What would happen if we were able to actually, I'm going to pause here for a sec. So far, we've talked about motions that are apparent, things that we see because of our own movement around the sun or around ourselves. I'd like to talk about real motion now for a little bit. And first of all, let's start with the sun. The sun, sometimes people don't realize, is always spinning. The sun is spinning around itself, and you can see that because you see those little dots, those what we call sunspots, that are buzzing around as the sun rotates. Even more so, stars move through space. If you were to look at the Big Dipper for many, many years, you're going to see its pattern change. Let's see that. So this is what the Big Dipper looks like today. And I mentioned it makes a nice shopping cart with a tail. These stars are moving in various directions. And in 50,000 years, we're not going to be around then, but perhaps some of our some of our offspring are. The Big Dipper is going to look quite different. And if we were to wait for a very long time, these constellations would be very different indeed, and maybe even unrecognizable. So let's go to the big time movement of our sun in our galaxy. This is a picture, what we think the Milky Way would look like from the outside. This is as good a guess as we have as what the Milky Way looks like. The sun is kind of midway to the edge, and the sun takes about a little over 200 million years to go around the galaxy once. This means that the last time the sun was here, there were dinosaurs. It was the early Jurassic period. So something like a Dilophosaurus would have been walking on the Earth, and there would have been no people whatsoever. So think about that. That's how long it took for the Earth to go around our galaxy once. We covered a lot of ground today, and I'm really interested in hearing the questions that you What a great question. From an astronomical point of view, the sun is going to enter Taurus, and I'm going to look it up because I don't want to make a mistake here. So it's May 13th. So technically speaking, you are Aries, just so that you know. And when the sun, as we discussed, when the sun enters Taurus, and it's probably close enough now, you can't see Taurus right now. I think you'd be better off if you waited a couple months on either side, and then you'll be able to see Taurus, which, by the way, looks like a nice sharp V. It's close to Orion. You'll be able to see it in a couple of months again. Nice question.
All right. Well, something to look forward to, Kyle. All right. Our next question comes from Miles J. Miles asks, how do people come up with the names of constellations?
You know, I get asked that. Sometimes I get people a bit frustrated because they say, what do you mean this looks like a ball? It doesn't really. And some of them, frankly, are even less obvious than that. People like to see patterns. They like to be able to organize the sky in a way that makes sense to them, in a way that connects to things that they care about. That's, I think, the fundamental reason why we like to see patterns. Our brains work that way. I recognize that some of them are really not so easy. And also, we should acknowledge that different cultures saw different things in the sky and might have seen something very different than others. Some, in fact, have even connected the stars differently. So if you don't see all the patterns very clearly, I wouldn't worry about it. They're pretty arbitrary, quite honestly.
Okay, great. Thank you. Okay, our next question comes from Tia, and she wants to know, are stars bigger than Earth?
Oh, nice question, Tia. Especially since we talked so much today about what appears to be true and what is true. Stars look so much smaller than the Earth, right? Because they're little dots in the sky. And even the sun doesn't look really anywhere close to as big as the Earth. But the fact of the matter is that if we could line up stars with the Earth near each other, we would see that stars are hundreds, sometimes thousands of times bigger than the Earth. So in reality, the Earth is a pretty small thing compared to practically any star in the sky.
Wow. Thank you. All right. Next question comes from Ryland. Do we all see the same constellations at the same time?
That's another great question. You guys are asking great questions. So Ryland, let me kind of differentiate here. The short answer to your question is no. If we said, okay, everybody, right now, let's everybody on the Earth zoom together, what constellations can you see? Well, first of all, half the Earth is only going to be able to see the sun if they're lucky, and the other half are going to be seeing all kinds of different things because it depends on your latitude. If anybody on the Earth is at, let's say, 43 degrees where Milwaukee is, all those people are going to see the same night sky at the same time, only when it's 8 o'clock my time, somebody halfway around the world is going to have 8 o'clock in the morning their time. So when it's 8 p.m. for me, I'll see the same thing as when they have 8 p.m. where they are. I hope that makes sense.
Very good. Yes, that does make sense. Very interesting. So our next question comes from Jerry M. How do astronomers come up with an estimate of the number of stars in our and other galaxies?
Great. Great, Jerry. So you use the same kind of technique that you would estimate, you would use to estimate how many people were in the ballpark today. And I realize there's going to be nobody at the ballpark. The estimation today is going to be easy. But when you have a full stadium, nobody is going to sit there and actually measure exactly how many people you have. Or if you have a festival with a lot of people on the street, nobody's going to actually sit there and count individual people. What you do is you look at a small, but not too small portion of, say, sidewalk that people are standing in. You would count those and say, okay, well, how many patches like that do I think I have? And multiply the number that you had for that patch by all the patches that you were looking at, and that will give you an estimate. Now, frankly, you can get pretty sophisticated with that kind of measurement. So lately, we've upgraded the number of galaxies that we think the universe has because we started counting galaxies that we couldn't see before. They were too small. We think they're about 1 trillion. That is 1 with 12 zeros after that. Great question.
That is a great question. Okay, our next question is from Iva. How many constellations are there?
Well, that's an easy question because we have taken the whole sky. We said, pretend it's a puzzle and cut it into 88 pieces so that each star belongs to one constellation and there are no orphan stars out there. So 88. And sometimes people will say, well, can we discover another one? Well, no, because we've tiled the entire sky. It's all spoken for. We might discover new stars, new galaxies, all kinds of things, but not constellations. Nice.
Very good. That was a great question. Thank you. Okay, our next question is from Tia K. How are the stars made?
How are stars made? Stars start in huge clouds of gas. And a cloud of gas might be sitting around in space for a long time until a fast wind from usually a star that just died slams into the cloud and gives gravity a little assist. When gravity gets assist, then the cloud starts shrinking. And eventually you can get the cloud to shrink so much that the center part, well, first of all, it's going to start having little dense areas, and each one of those is going to get so dense that you can start fusion. And now we're going to talk next time about that. How do you get stars to shine? When it gets dense enough and hot enough, stars can start shining. And since this is a kind of an important concept and a little time consuming, I'm going to hold off for the rest of that for next time. But thank you for giving me such a nice lead for next week's program.
All right, way to go, Tia. All right, our next question comes from Nasika. How far into the galaxy can we see with a modern telescope?
Well, so I happen to know this name is pronounced Nafsika.
I'm sorry.
This is a friend who's actually joining us from Greece today.
Oh, boy.
How far into the galaxy, yes, Nafsika, how far into the galaxy can we see with a modern telescope? I'd say let's start just with the naked eye. With the naked eye, you can see about 2,000 light years away in our own galaxy. So if you imagine the Milky Way as being a nice round pancake, we live somewhere here. The pancake is thin. We can see to the edge of the disk of our galaxy. Now, if you have a telescope, you can see almost to the very center of our galaxy. The problem is, remember those clouds I talked about before? Those clouds actually block some of the light that we could see. So if it's a visible telescope, we can probably see only about 15,000 light years or so toward the center of the galaxy. Now, if you have a radio galaxy that sees through all that gas and dust, you can see billions of light years way past our galaxy. Great question.
Very good. Thank you. All right. Our next question comes from Nicole. Why are stars different colors?
Why are stars different colors? Stars are different colors because they're different temperatures. So the hotter the star, the bluer it is. The cooler the star, the redder it is. And just remember, that's opposite from your tap. Normally, when you see blue, it's cold, and red is hot, but stars are the opposite. There are other reasons why stars might have different colors, but this is the most important one. They have different temperatures. Great question, Nicole.
Good, thank you. All right.
Well, I guess we had such a wonderful set of questions. I would like to point out that it's not always possible to get to all of them in the kind of time that we have. So we are going to have that mailbag where we're going to try and answer as many of those questions that we didn't quite get to. And I will be sending you an email with all the activities that I mentioned and a couple more actually, so that you can try some stuff at home and think about the constellations. And I do hope that you join me next week where we talk about the brightness of stars and how do stars make light in the first place. Thank you so much for listening and for contributing. I really enjoy having this conversation with you. Thank you.
Thanks again, Dr. Creighton. We really appreciate everything that we learned today. And remember, kids, when you get outside, look up. I have just a couple of announcements before we break today. I wanted to let you all know that today is the last day to enter the UWM Alumni Association's first coloring contest. This is for kids and adults, in other words, kids of all ages. You can download your coloring page at this site, alumni, spelled alumni.uwm.edu/coloring contest. My second announcement, we hope that you can join us for our next episode. Like Dr. Jean told us, it's called How Much Do Stars Shine? It will be on Friday, May 8th at 10 a.m. That's Central Standard Time, the time here in Milwaukee, Wisconsin. And lastly, if you missed last week's program or you want more information about our future Panther Academy, please visit us. You can find that information at alumni.uwm.edu/ www.uwm.edu/Future Panther Academy. Thanks again for everyone who joined us today, and hope to see you next week. Bye!